Okay, time to talk about proof methods, which is how we harness all of this logic that we've been looking at, the connectives and the quantifiers, to actually, come up with a strategy for proving stuff, because that's what math's about. At least that's what the math in this class is about. Applications, take another class. All right. You'll have noticed that most of the things that we have been thinking about in this class are propositions of the form for all x in some domain of discourse, some p of x implies q of x, right? If something, then something else. So this has a name, this type of statement. This is called a universally quantified implication. For reasons I hope are clear. We've got a universal quantifier in front of an implication. And let me give you an example of something that we looked at. This is one of the theorems in the chapter and section on matrix inverses. I forget the theorem number off the top of my head, but we've got theorem for all square matrices A. If A is non-singular, then A transpose is non-singular. And in fact, we could make the then piece a little bit more exciting. We could start wrapping in other connectives, right? We actually proved a little more. We said that A transpose is non-singular, and the inverse of A transpose is the transpose of A inverse, which exists because A is non-singular. So there you can see actually the form of this is for all A in the set of n by n matrices. A inverse exists. That's one way of saying A is non-singular, implies A transpose inverse exists, and A transpose inverse equals A inverse transpose. Right? And like the point of all this logic stuff is, I think we probably wrote down a proof, or there's a proof in the book. And how do we know that that actually does the job in showing that this statement is a true statement? So let's think a little bit about how we would prove this thing. So some proof ideas. We start with a universally quantified statement with an arbitrary element in the domain of discourse. And so that might, for the formal statement above, we might write, let X in D. And for the matrix theorem up above, we would write, let A be a square matrix. Or let A be an element of the set of n by n matrices. Either one of those is fine, right? So we start by taking an arbitrary element of our domain of discourse. And that way we know what we mean when we look at P of X, Q of X, and what we need to do to show that P of X does imply Q of X. All right, so having picked X in our domain of discourse, P of X and Q of X are both statements, and they have truth values. So true, true, false, false for P of X, true, false for Q of X. And we know when an implication is true. It's true when both parts are true, when both parts are false, when the premise is false and the conclusion is true, and it's false when the premise is true and the conclusion is false. Okay, so we want to show that this statement is true, and there are a couple ways that we could do this. So notice a couple things here. If P of X is false, the statement is automatically true. the implication, I'll say the statement, by which I mean the implication, is automatically true. So we don't really need to worry about the case where P of X is false. If it is, there's nothing to show, because the way that the implication is defined as a logical connective means that it's automatically true when your premise is false. And so the only real work we have to do is assume if P of X is true, then we need to show that Q of X is also true. So that's why most of our proofs that we've written so far look like let X and D, if P of X, blah, 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 do some math, therefore Q of X, and that makes our proposition true. So the work in this case, thinking about it this way, if we want to start with P of X, is showing that that when P of X is true, we can do some math to show that Q of X must be true, and therefore P of X implies Q of X. And this is called a direct proof technique. Let X be in the domain of discourse, assume P is true. Usually we just say assume P of X, by which we mean assume P of X is true. We do some math or logic, whatever it is that we're using our logic for, but in this case it's math, and we conclude with, therefore Q of X is true. And that's how we know that we've got a proof, right? We showed P of X being true means Q of X has to be true, and therefore the implication is true. If we started by saying assume P of X is false, the next line would be thus the implication is automatically true because that's how it's defined. So we don't bother rating it. All right, so that's direct proof, but since it has a name, you might guess, because you're good at professor psychology here, you might guess that there are other techniques for proof. So we have indirect proof techniques. And let me start by grabbing the truth table again, and then I'll do some examples here. Actually, let's look at this thing called proof by contrapositive. So remember that the contrapositive of P implies Q, and I'll make this our propositional function P of X. P of X implies Q of X. That's logically equivalent to not P of X. I got it backwards. Not Q of X. I was starting to write down the inverse, I mean the contrapositive. So not Q of X implies not P of X. And so we can use this to figure out another proof technique. So let's look at P and Q here. I dropped the of X. I hope you'll forgive me. So P can be true, true, false, false. Q can be true, false, true, false. And the contrapositive, not Q, implies not P. If we think about when this statement is true, well, whenever not Q is true, that means, or whenever not Q is false, the premise of this implication is false, it will be true, which means whenever we see a true in the Q column, this thing will be true. And it will be true when not Q is true and not P is also true. So, I think I got that one already. So this is the one I meant before. Okay, so whenever I have a true in the Q column, that makes not Q false, and implications are true if their premises are false. When both of pieces are true, our implication is true. And so the false happens when P is true and Q is false. So a proof technique by contrapositive is going to look like this. Let X be an element of the domain of discourse. Assume Q of X is false. Or alternately, you could say assume not Q of X. And parenthetically, we mean not Q of X is a true statement. And actually, this is the one that you'll see most commonly. I'll box it off. So usually we see assume not Q. Then there's some math, blah, blah, blah. Therefore, not P of X is true. Or therefore, P of X is false. And that's the end of our proof. Because again, if we assume that Q of X is true, automatically our implication not P implies not Q is also going to be true. So there's nothing to do there. So proof by contrapositive, sometimes it's a little bit easier to do a proof by contrapositive. And the last thing I will give you is proof by contradiction. And then I will do some examples of the proof techniques, and I will highlight how I know which proof technique I'm using. Proof by contrapositive, and then proof by contradiction. So this one is a little bit involved. You're going to want to remember your law of implication here. So remember that the law of implication says that P of X implies Q of X is logically equivalent to not P of X or Q of X. So that's our law of implication. I think that's part A. Which is equivalent to, let's whack this with De Morgan's and the double negative. So I'm going to negate both pieces. When I negate a not P, I'm going to get a P of X. That's my double negative. My or turns into an and. My disjunction becomes a conjunction, and I get not Q of X. And so I want to show that P of X implies Q of X is true. And what I can do is I can assume that it's false and show that it leads to a contradiction. And so it must be true. So the idea here in a proof by contradiction is you assume P of X and not Q of X is sorry, I see what I did. I was like, wait, but that's right. So I want negations around all of this. Boop, boop. Okay, so when I negate that last statement, that's actually where I get to. So if I show that this is false, or assume that this is true, I want to then show that you get a contradiction. And conclude that P of X and not Q of X must be false, which by the logical equivalences up above, if we negate them all again, or if we just think about what happens when we do these truth values, if this is false, the negation of P implies Q is false, which means P implies Q is true. So P of X implies Q of X is true. So proof by contradiction is going to look like, let X be an element of our domain of discourse. That's so that our propositional functions P of X and Q of X actually make sense. We know what we're talking about, right? You don't want to get a comment from me saying, but what are you actually talking about? It means you haven't told me what your domain of discourse is and what your elements are. we assume P of X and not Q of X is true. We do some math. And this is a little hard because we don't exactly know what we're aiming for. It's not like there's, you know, some specific statement that we want to get. And sorry if you hear the rustling. Of course, Bad Cat Sophie has decided this is the good time to join us. Anyway, we do this, we mess around with this, and we get to some contradiction. You know, maybe something like 0 is equal to 1. Or, you know, A inverse is the 0 matrix. That would be a contradiction. Something like that. Something that's just not possible. And that's the end of our proof. Because now that means that the original implication must be true. So let me give you a few examples of proofs, and we'll look at the proofs and we'll decide which proof technique I was using based on what I wrote. All right, here is a proposition. It says for all integers A is even implies A squared is even, or if A is even, then A squared is even. And I've written the beginning and end of my proof here. And I want to see if we can identify which proof technique I'm using. So I've let A be an integer, right? That's saying, all right, my domain of discourse is the integers. So let me pick an arbitrary one. I'm assuming that A is even. This is the premise of my implication. And I get down to a point where, so that I'm saying my premise is true. And I get down to a point where I show that A squared is even, which says my conclusion is true. And so from the first and last line of this proof, we can identify this as a direct proof. And what's going to happen in the middle is that's where the math goes, right? So I use the fact that A is even to get down to a point where I can show that A squared is even. So let's do the math in here. Let me get a slightly darker color. Well, being even, this means that A is equal to 2k for some integer k. That's the definition of even. It's, you know, divisible by 2. It's 2 times some number. Now consider A squared, which is going to be 2k squared, which is, it's 4 times k squared, but I'm going to factor it out and make it look like 2 times 2k squared. And 2 times k squared is an integer, which means that A squared satisfies the definition of even. It looks like 2 times some integer. Therefore, A is even. All right, cool. So I even magically left the right number of lines in this proof. I wasn't sure I was going to do that. Okay, so there is an example of a direct proof. All right, we've got a new proposition now, and in fact, it's the converse of the previous one. It says for all integers A squared is even implies A is even. So if A squared is even, then A is even. Let's look at the way the proof starts and ends, and then we'll see if we can fill in the math in between. I started by letting A and Z. No big shock there. I'm assuming that A is odd, which means I'm assuming that my conclusion is false. And then I get down to the bottom and I see, therefore, A squared is odd, which means I'm showing that my premise is false. And when I assume that my conclusion is false and use that to show that my premise is false, this is an indirect proof, and in fact, it's a proof by contrapositive. So when you're writing a proof by contrapositive, you don't really need to say like, you know, we're proceeding by the contrapositive. You can just like tell me what you're assuming. Your last line should be what you get to, and I'll be able to know that you did a proof by contrapositive. And any mathematician will be able to know that you've done a proof by contrapositive. So let's see if we can get the math in here. All right, well, A is odd. This means that A is 2k plus 1 for some integer k. Right, so odd means you look like a an even number plus 1, right? You're 1 away from an even number. And then I'm going to make this as parallel as possible to our previous proof, because I think I'm going to end up using the same number of lines here. So now consider a squared looks like 2k plus 1 squared. And, oh man, I didn't use the same number of lines. Geez, Professor Gibbons. All right, I'm going to continue on this same line here. I'm going to square this out. So I would get, let's see, I would get 4k squared plus 4k plus 1, which I can pull a 2 out of in my head. So I really want it to look like 2 times an integer plus 1. And it's going to look like 2k squared plus 2k. And you can check if that foils out that way. And 2k squared plus 2k is an integer, which means that a squared looks like 2 times an integer plus 1, and that's the definition of odd. Therefore, a squared is odd. And I'm done. That ends my proof by contrapositive. All right, one more proposition, and the smart money's on. This will be a proof by contradiction, but let's see if we can figure out why. All right, first of all, the proposition is the number square root of 2 is irrational. And that, as written, does not look like a universally quantified implication. So what we can do is we can rewrite it. We can say for all real numbers x, if x squared is 2, then x is irrational, right? What it means to be the square root of 2 is that you square it and you get 2. And when we're thinking about the number square root of 2, we're really thinking about the real number. We're not thinking about potential complex numbers or anything like that, right? So for all real numbers x, if x squared is 2, then x is irrational. And let's look at the first line of our proof. It says, all right, let x and r, okay, no big surprise. Assume x squared equals 2. So we're assuming our premise is true. And we're assuming that our conclusion is false. And that is how you start a proof by contradiction. One of the nice things about a proof by contradiction is you get to assume as much as possible. And one of the tough things about proof by contradiction is down here by the end of proof symbol, I'm not exactly sure ahead of time what the contradiction is going to be. It probably takes a little bit of monkeying around to see like what goes wrong when I do this. So let's actually do the math for this one. It's kind of a fun one. So in order to be, all right, in order to be irrational, or to be rational, this means there exist integers p and q not equal to 0, where x can be written as p over q. And we can assume that p and q have no common factors, right? That we canceled away anything until we got down to, you know, the fraction with no common factors between the numerator and denominator. All right, well, let's see what happens. If we have this, then we have x squared is 2. That means that p squared over q squared equals 2. I don't know why I displayed that in a new line. Let me just do that in line. Come on, Gibbons. And they let you teach writing intensive math courses. All right, it means p squared over q squared is equal to 2. And therefore, p squared equals 2 times q squared. All right, now we have that p squared is an even number, and our previous proposition, see how sneaky I was? I proved something that was going to be useful. By our previous proposition, p is also even. I guess I could make that clearer. So when on the previous line where I say p squared equals 2 times q squared, we have that p squared is even. All right, well, what does this mean? This means there's an integer k where p looks like 2k. Thus, if I substitute that in up above, I've got 2k squared equals, well, sorry, the quantity 2k squared is equal to 2q squared. And we can expand this. Can expand the left side a little bit to obtain 2 times 2k squared, same trick I used up above, is equal to 2q squared. So that 2 times k squared is equal to q squared. Right, I just canceled off those 2's. And that means that q squared is even. So we have that q squared is even. And therefore, again, by the previous proposition, q is even. But this contradicts. That p and q shared no common factors because now they share a factor of 2. And that's it. That's our contradiction. So therefore, the square root of 2 is irrational. Didn't do such a great job on the paper usage there, but that's how proof by contradiction goes. Again, I think that direct proof and proof by contrapositive are a little bit easier because you know where the math starts and where it's got to end so that you know where you're starting and where you're going. And proof by contradiction is like, all right, I'm going to assume as much as possible and do some math and hope for a contradiction by the end. But those are the 3 big proof techniques. And what I'm going to show you next are a couple other useful logical equivalences for working with certain types of implications. So let's take a look at some other logical equivalences. Other useful equivalences. And this one doesn't have a name. I wish it did, so I'd like to refer to it by name. Maybe it doesn't, I just don't know it. So let's say that we're proving something like for all x and d, p of x implies an or statement, q of x or r of x. Now that statement on its own is a little bit hard to deal with because if we are going about a direct proof, we assume p is true and then we need to show q of x or r of x is true. And there's like 3 different ways that that statement could be true. So that kind of seems like a lot. So let's see what we can do using the law of implication, and then maybe we'll get lucky and some other laws will apply here. So this says that for all x in D, well, we apply the law of implication here and we get, let's see, we get p of x and let's see, sorry, I was daydreaming for a second. I was thinking about cats, no big surprise. All right, law of equivalence says not p of x or q of x or r of x. So we've got now 3 ors. And we can manipulate the first one for all x and D we can apply the law of the double negatives. We can not that guy. That's not, ooh, it's a lot of knots. Not P of X or Q of X. I don't know where to end my parentheses. Bump, maybe one more, or R of X. And what we get now is, let's see, so we've got for all X in D, we can turn this first one into an and, so we're going to get a not. The double negative of P of X is P of X. We get an and, not Q of X. Or R of X. And look, we've got not something or something, and that's law of implication again. So we get for all X in D, P of X and not Q of X, not Q of X, implies R of X. So to recap what we did here, we used the law of implication on the first line. On the next line, I did a sneaky double negative. I introduced some negative signs. And that was really so that I could use De Morgan's. And then I used the law of implication again. And so this logical statement that was a little bit hard to work with, we're assuming P of X, and then we have to show that this OR statement, which has two component propositional functions, is true, right? That's a little bit, I don't know, feels like the balance of what I know and what I need to show is a little off. We got down to something where I get to assume P of X is true and Q of X is false, and now I just need to show R of X. It's also equivalent to, we can switch the role of Q and R, so we could say for all X in the domain of discourse, P of X and not R of X implies Q of X. All right, again, I'm not exactly sure where all those parentheses went. And you'll see some examples of things like this on your writing assignments. So this is going to be like, prove that this implies this or this. And you're gonna wanna, trust me, you're gonna wanna rewrite this as, okay, proof, let P of X be true, Q of X be false, math, therefore R of X is true. So that's another equivalence. I don't have a name for it, but it will come in handy. And then the very last example that I want to, or very last thing I want to talk about is how do you show a universally quantified implication is false? So maybe you've come up with a conjecture that's like, for all square matrices, if this, then that. And then you realize, oh, I don't think that's true. How are you going to convince somebody else that it's not true? So we start with a universally quantified implication for all X in D. P of X implies Q of X. So showing that that's false is equivalent to showing that its negation is true. So we want to show this is true. Show that this statement right here with the not in front of it is true. And let's take, I'm going to take my own advice here, which is rare. But I gave you the advice that said, if I'm working with the negation of a statement, I want to try to get that negation as far to the right as possible to make the statement, hopefully, probably, in its easiest to think about form. So first of all, I remember that negating a universal quantifier gives me an existential quantifier. So there exists an X in the domain of discourse such that, and I move the negation over here such that it's not the case that P of X implies Q of X. And it's probably going to be easiest to think about if I continue to move that not to the right, and I can use one of my laws of implication to do that. So I have x in the domain of discourse such that p of x and not q of x. And this is what I want to show is true. So I've gotten down to the point where I want to show there's some matrix where p of x is true and q of x is false. And the way that I do that is I construct a counterexample. And I'll give you an example of what writing an example looks like. It's a little meta here, but let's say that the statement, maybe we made a conjecture one day that for all square matrices A, if A is non-zero, that implies that A is non-singular. Well, I want to show that this is false, and I'm going to show that it's false by showing you some non-zero matrix that is non-singular. So here's an example, and we would write it like this. So one way that you could start is saying it's not the case that every non-zero square matrix is non-singular. So what I did was I literally wrote out the negation of our conjecture. It's not the case that every non-zero square matrix is non-singular. Indeed, the matrix A equals 2613 is non-zero, but in class, we showed it does not have an inverse. And that's the end. We came up with one example of a matrix that's non-zero that doesn't have an inverse. And that's all we had to do to show that there are some non-zero matrices that are singular, that are not non-singular. And I'll give you a little tip if you're writing this up in tech. In the writing assignment preamble, I've defined the environment example star for you. And you would, put in your text, and then at the end of your example, you'd write end example star. And notice there's no proof here. There's no end of proof symbol. Examples are pretty conversational in math, because usually our examples that we're giving are counterexamples to some statement, and all we need to do is show that there's something out there that, does this thing that we need it to do. So in your LaTeX, you can just make an example, pretty conversational, usually just a paragraph. You can be a little bit less formal, which I'm sure will be a break after all of the formal proofs that we've been writing up. And so there you have it. We've got our overview of logic. We talked about connectives, which were the ways that we could connect statements together to make more interesting statements like and statements, or implications, or combinations of those things. We have our quantifiers, which let us know what are you actually talking about, so we know what things apply to. And then we've got our proof techniques. If we want to prove a universally quantified implication, we can use a direct proof, a proof by contrapositive, a proof by contradiction. If it's one of these very special types of implications where the conclusion is an or statement, we've got this logical form where we can kind of move stuff to the beginning of the implication. So if we're doing a direct proof, we get to assume as much as possible. We say assume p of x and not q of x. Math, 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 math. R of x is true. Great. And then for those rare cases where you're looking at a prove or disprove, if you find that some universal statement is not true, all you need to do is give a little counterexample to show here's something that violates that rule. And that is the overview of logic. as far as we're going to use it in our linear algebra class, I will say that Hamilton has a quite awesome symbolic logic class, and you should consider taking it if you found this stuff kind of cool and groovy. All right, that is our unit on logic. Lots of examples for you to do in the logic packet, plus some other examples in the homework.